Hey guys, so this week we are focusing on plate tectonics. So we're moving away finally from talking about minerals and rocks. And now that we understand the three different classifications of rocks and how rocks are formed on Earth, we can sort of move on to different topics, right? So this week we're going to talk about plate tectonics and how plate tectonics is related to the interior of the Earth. It's related to mountain forming processes. And so we're sort of moving away from this understanding of the sort of solid bits, right? We're still going to be talking about the geosphere this week, and then we're going to move on into basically a new section of the class where we talk more about the hydrosphere and then the atmosphere. So we are sort of, finishing up the geosphere, and we're talking about one of these really important aspects of the geosphere, which is this concept of plate tectonics. And so let's go back and review this slide from the very first week of class, which is, remember that the geosphere is the solid part of Earth, right? This is Earth's rocks. And so we focused on our three different classifications of rocks so far. And then remember from the first week of class, we talked about that Earth is a differentiated planet. And what that means is that Earth's interior can be separated into different layers, or essentially is separated into different layers, which we describe based on their chemical composition or their physical properties. So there's actually two different ways that we can separate Earth into different layers. And the first way that we separate Earth into different layers is based on chemical composition, right? So based on the chemical properties, right, the chemistry of these layers, we divide the Earth into the crust, the mantle, and the core. And probably when you were in middle school, this is really what you focus on. I know in elementary school when you learn about the Earth, these are like the three main ones you learn about the compositional layers, right? The crust, the hard outer layer, right? The mantle, and the core. And that's based on basically the percentage of chemicals, right, that are making up each one of these, right? What percentage of minerals is making up each one of those layers. And then we can also talk about Earth's physical layers, right? So layers of Earth that are divided by how they behave physically. And so those are a little more what I would say these are like more scientific sounding words, right? Where we talk about the rigid outer lithosphere, the plasticky asthenosphere, the middle mesosphere, which is solid, the liquid outer core, and the solid inner core. And so specifically, let's think a little more about this chemical composition, right? So again, dividing the Earth into layers based on the chemicals that the rocks there are made up of. So our crust is our outermost layer. So up to about 75 kilometers depth in the Earth. And the crust is made up largely or of a higher percentage of silicate minerals, right? So remember that silicate minerals are largely the types of minerals, right? Rocks that are made up of silicates are largely what we see at our surface, right? It's just like the biggest sort of class of rock forming minerals. And right, we see these at our surface because our crust and our mantle are made up of those, right? And so the crust is dominantly made up of granite, andesite, and basalt. So specifically, our continental crust is made up of those more felsic to intermediate rocks, are granitic and our andesitic rocks. And our ocean crust is largely made up of basaltic or more felsic rocks. And this dominant composition of the crust and the difference between continental and oceanic crust is related to how those two crusts form. Essentially, the source, right, of the magma that forms ocean crust versus continental crust. Additionally, a lot of continental crust, right, is thicker. So, right, continental, oceanic crust are distinctly different. We will talk about the differences between continental and oceanic crust again later in this semester when we focus more on ocean processes. That middle layer, the mantle, is about 75 to 2,900 kilometers deep, and the dominant chemical composition of the mantle is peridotite, which again is, right, basically a silicate mineral composition. But remember that peridotite is ultramafic in chemical composition, right? So we're moving, as we go deeper and deeper into the earth, we get higher and higher abundances of iron and magnesium rich chemical composition. So the cool thing about the mantle is that it's basically the largest portion of the earth, both in volume and in mass. So the crust is right, this thin outermost layer. The majority of the earth is the central mantle. And then the core is our innermost layer. This is between 2,900 and 6,370 kilometers depth. And the dominant composition of our core is metallic iron. And because it's made of iron, it's very dense, which means that even though it only makes up about 16% of Earth's volume, it makes up 32% of the mass of Earth, right? Because we have this really dense iron in the core, right? So if we're going to divide the Earth into layers based on chemical composition, we classify the crust by all of our silicate composition ranging from felsic to mafic. Then our mantle is where we have dominance of our ultramafic silicates, and then the core is where we have dominance of metallic iron. So if we switch to defining these layers based on physical properties, what we see is our outermost layer is the lithosphere. So remember that prefix lith means rock. So this literally gets translated as the rock sphere. And so the lithosphere is the rigid, solid, and strong outer layer of Earth. And so this includes both the crust and the upper mantle. So notice that even though we say the crust and the mantle are different things based on chemical composition, based on how they behave physically, right? Because this has to do with that confining pressure that we talked about last week with metamorphic rocks. Notice that chemical composition doesn't play a part when we talk about the physical properties. So think of the chemical properties and the physical properties as being separate, even though when we lay them next to each other, they correlate a little bit. Because chemical and physical properties are related to each other a little bit, but think of them separately because the top of the mantle is under enough pressure, right? And it's not too hot, right? So it's sort of at this Goldilocks place where it's under enough pressure and it's not too hot that it's not quite melty yet, right? And so the upper mantle is included with the crust when we talk about the solid, rigid outer layer of the Earth, which we call the lithosphere. Underneath the lithosphere is the asthenosphere, which you can translate as weak sphere. This is where temperature is just right, that the rocks melt a little bit, right there. And don't think of them as like a liquid. Think of them more as like a putty, right? A plastic. It's you can deform it and it's flowing very slowly, but don't think of this as like a liquid, right? That's just like flowing underneath Earth. Sort of classically, when in elementary school, a really cool thing, you know, that elementary teachers do when they talk about plate tectonics is they like use Oreos, right? And so the white part of the Oreo is the asthenosphere. So think about like how you can kind of smush that and deform that around, right? And then the outer cookie part, right, is hard and rigid. And so our asthenosphere, this is part of the mantle where temperature is just right for the rocks to get a little plasticky, a little melty, and deform. And so why we care about these two physical layers specifically is that when we're talking about plate tectonics here in a bit, as we get to what plate tectonics is, we will refer back to these two layers, the lithosphere and the asthenosphere. So remember, lithosphere is the rigid upper part, right, outer layer. The asthenosphere is this plasticky, easily deformed part of Earth. Next layer is the mesosphere, literally means the middle sphere. Anytime you hear meso, right, like mezzo soprano, that means middle. And so this is where we are deep enough in the Earth that even though temperatures are increasing the farther you go down in Earth, the pressure is high enough to offset that temperature. And so the mesosphere is solid, and it's more solid, more rigid than the asthenosphere is. As you go deeper, we get to the outer core. The outer core is liquid, and that's because the temperature specifically from the inner core, which is solid but is radiating a lot of heat, right, makes the outer core look very hot so that it's liquid, right? Even though there's an immense pressure, the temperatures are too immense, right? That pressure isn't able to offset it. So think of the outer core again as a liquid. And then our inner core is solid, right? And our inner and our outer core are both the iron-rich chemical core. And as we lose heat from the inner core and Earth rotates, we get convection, right, movement of this liquid in the outer core, which actually generates the Earth's magnetic field. The Earth's magnetic field is why that we are able to use a compass to find north. And it is also the reason why we are protected from a lot of radiation from space. All right, so this lecture, we want to understand the development of plate tectonics as a theory and the mechanisms and parts of the tectonic system. So actually what I'm going to cover today is like the mechanisms and parts of the tectonic system. And then as our lab, I believe it's next week, we will do an activity related to how the theory of plate tectonics developed and a lot of the evidence behind it to support the theory. So today I just want to cover sort of the main mechanisms and parts of the tectonic system and tectonic plates. And then in lab, we will do an activity surrounding, right, the development of this theory, because it's sort of one of these big points in time when geology, like as a science, kind of got turned on its head because, right, plate tectonics wasn't always a theory and it wasn't accepted until about the 1950s. And so geology processes, right, the way that scientists thought about geology and geologic processes changed immensely with the acceptance of the plate tectonics theory. And so it's sort of like an interesting history of science lesson, right? And it's sort of a classic example that we'll cover in lab. So right now we'll just talk about the mechanisms and the parts of the system. So first, like, what is this word tectonics, right? So tectonics is just the origin and arrangement of the structural features on Earth's surface and the study of those things, right? So geologists want to understand, like, why are there mountains here? Why are there continents here? Why are there ocean basins here? Why are there mountains in the bottom of the ocean? Like, why does the Earth broadly on the surface look this way? And planetary tectonologists, right? So people who study tectonics of other planets, right, using like imagery or probe data, right? They do the same thing. They try to study the origin and arrangement of the structural features, right? How did these features on the moon form? How did these features on Mars form, right? Et cetera, et cetera. So plate tectonics then is like related to the study of the arrangement and origin of the structural features on Earth's surface. And it's this specific explanation, which is a theory that the Earth's surface is divided into a few large, thick plates of lithosphere. So remember that lithosphere is that solid, rigid outer layer made up of the crust and the upper part of the mantle. And these thick pieces of lithosphere that are broken into a couple dozen pieces move slowly across the surface. They ride on top of that plastic asthenosphere, and they change in size relative to one another over time. They move around, right? And so that movement of these big, huge plates of lithosphere on top of the asthenosphere, change in size, make these surface features, right, like mountains or ridges or trenches on Earth. So here, what is a plate? Plates are the large, irregularly shaped pieces of the lithosphere. We have about 12 main plates and then some smaller plates as well. And remember that the lithosphere makes up the crust and the upper mantle, and that the lithosphere rides over top of the asthenosphere. Remember, the asthenosphere is the part of the mantle that is a little bit plasticky, right? It's a little bit melty. It's not a liquid, but it's a little melty. It's easy to deform. And so what happens when you put some weight on top of the lithosphere, the lithosphere can bend a little elastically when you put some weight on top of it. And that actually causes, right, that load weight then gets offset into the asthenosphere. And that causes the asthenosphere to move or flow. And as the asthenosphere moves or flows, that moves the plates of lithosphere around. So we talk, the words that we use to talk about that are that the asthenosphere flows plastically when it is loaded with some weight. And we have two main types of lithosphere. The first is continental, as I hinted at earlier. Our continental crust is largely made of silica-rich felsic minerals. And because it's made of felsic composition, it's generally lighter or less dense and thus more buoyant than the second type of lithosphere, which is oceanic. So continental lithosphere is thicker, but less dense than oceanic lithosphere. Oceanic lithosphere's composition is more mafic, right? Has higher magnesium and iron in it, related to the provenance, right? Where the magma to form these pieces of lithosphere came from, right? The source for oceanic lithosphere is deeper in the mantle, right? Because it's heavier, it sinks lower. And so because the oceanic lithosphere, the source for it is lower in the earth, it has higher amounts of magnesium and iron. So oceanic lithosphere is thinner, but it's more dense and thus heavier and thus less buoyant. And so it sinks lower into the mantle. All right, so as I mentioned, we have about 12 major plates. In lab, we will also sort of work on labeling these plates and seeing how they move relative to one another. But the important thing to note is that most of the plates are sort of broken up based on whether there is a continent or an ocean associated with them, right? So we have the North American plate, which North America, part of Greenland, part of Russia, right, is on this plate. We have the Pacific plate, which is the Pacific Ocean largely, right? Australian plate, Australia is associated with that. Eurasian plate, where we have most of Europe and Asia. African plate, South American plate, right? And then notice, right, we have the big main ones, and then we also have some smaller ones as well. All right, so as we're thinking about plate tectonics, and I'll go back to this slide really quickly. Notice there's some red arrows on here, but for example, in North America, notice that we have one plate boundary along a coast, and along our other coast, we don't have a plate boundary, right? Because the plate boundary is farther out in the ocean. And because of this, we have some words to describe that relationship, which we call continental margins. And continental margins, right, this is where land meets the ocean. And if you have a continental margin that is near a plate boundary, like on our west coast, we call these active continental margins because they're near a currently active plate boundary. And margins far away from plate boundaries, we call passive continental margins because they're far away from these boundaries. And this is important because active continental margins are what we call tectonically active. So because they're close to plate boundaries, they commonly have more earthquakes and volcanoes. And passive continental margins are what we call tectonically stable, which means they have relatively few earthquakes. They don't have volcanoes. They typically have a more calm environment where you have like sand able to build up, sediments able to be deposited and turned into sedimentary rocks. And they typically tend to be more like sandy deposition dominated beaches, where active continental margins typically tend to be like erosion dominated shores. And when we go back to oceans, when we go to oceans in a couple of weeks, we'll come back to this active versus passive continental margin. The important thing to know right now is that just because we talk about continental and oceanic lithosphere, it doesn't mean that just like North America is its own plate and just the Atlantic Ocean is its own plate, right? We divide the plates based on, right, where like the continents are on plates, but you don't just have to have a plate boundary surrounding your whole continent. You can have oceanic and continental lithosphere on the same plate. All right, so I gave you the answer to this already because we're not in class, right? But you can think about the East Coast of the US. If we have relatively few earthquakes there, no volcanoes, like nice sandy beaches, then that means that the East Coast is a passive continental margin. Cool. Final sort of topic to talk about for lecture today is the three types of plate boundaries that we classify in geology. So we have three kinds of plate boundaries that define the three fundamental kinds of deformation and geologic activity associated with plate tectonics. So the first type of plate boundary is divergent. At divergent plate boundaries, this is where we have plates moving away from each other because we have some zone of tension, which means we have forces pulling apart. So when you have tension, right, like you pull on a rope and you put tension on the rope, that's when you have two forces moving apart. This is where our plates are splitting and moving away from each other. At our convergent plate boundaries, this is where we have two plates coming in contact with each other, colliding with each other, coming towards each other. And there are three different types of convergent plate boundaries, which we'll cover here in a second. And then at transform fault boundaries, we have two plates. They're not coming together or moving apart. Instead, they're just sliding next to each other, because here we have shear forces. Shear forces are when we have two forces going parallel in opposite directions to each other, right? So two forces moving past each other. And so because we have this shearing force, then we have plates sliding past each other, but they're not diverging or converging with each other. So divergent plate boundaries are when plates move away from each other. Convergent plate boundaries are when plates are moving towards each other. Transform fault boundaries are when plates are sliding next to each other, right? And so because Earth is a sphere, we have to have these places of transform faulting, right? Because if you've ever like tried to put a piece of paper around a ball, right, it doesn't really work very well, right? It gets crinkled. And so that crinkling, right, where we can't just go apart and together, we have to have some crinkling, which would be our transform fault boundaries. Okay, so at divergent plate boundaries, this is where we, again, have the movement of plates away from each other. The important thing to note is this can happen, and it starts on continents, but it's pretty rare to see active divergence on continents because basically because our planet is covered in so much water. It's very rare to see continental rifting, but we do see it in Africa and a little bit in Greenland. And so as crust is stretched, right, we have this force of movement away. We can have rifting or separation of a continent. And as that continent moves away from its, splits apart very slowly, then you start to form what we call a rift valley. And eventually that rift gets so large that you start to inject basaltic magma into that system. And eventually you create a new ocean basin. And so when we have continental rifting happen, right, long enough, right, and we sort of make a weak part in the crust that then can be upwelled by magma, as soon as we start to get like creation of basaltic magma, then we start to form an ocean floor. And we start to form new oceanic crust and new lithosphere. So eventually the ocean basin becomes wider and wider, and at what we now call a mid-ocean ridge when it's underwater, right? When it's on continents, we call it a rift valley. Underwater, we call it a mid-ocean ridge. And so at our mid-ocean ridges, at our divergent plate boundaries, we are creating new lithosphere because the plates are moving away from each other and magma is upwelling from underneath and being deposited, hardening, creating new lithosphere. Right, so here's an example of an oceanic spreading center called the mid-ocean ridge. You can see our North American plate and our Eurasian plate here on the map are moving away from each other. And along this boundary, we are creating new oceanic lithosphere. Right, so as the oceanic lithosphere spreads apart, new seafloor is created through volcanic processes. Because we don't have any like plates going like deep within the earth here, they're just moving away from each other. We get shallow earthquake focus depths. So at our convergent plate boundaries, this is where we have two plates running into each other, right? Two plates coming together, two plates converging. We have three different varieties. When we have an ocean plate and an ocean plate converging, what happens is the more dense oceanic plate subducts or goes underneath the less dense lithospheric plates. And what happens is we form an ocean trench right here. And we form what we call volcanic island arc. Right, so we form some volcanic island chains. When we have oceanic crust and continental crust converging, the oceanic crust is always going to be more dense than the continental crust. And so the oceanic crust subducts or gets pushed underneath, pulled underneath the continental crust. Again, we form an ocean trench, and we form volcanic mountains on our continents, right? So because this is continental crust, we form volcanic mountains. And then with continent-continent convergence, because continental crust is so thick, basically neither one of them can be subducted, and they just sort of run into each other and crinkle up. And when the two continental plates run into each other and crinkle up, we call that collision. And we form very large mountain chains when we have continental convergence. So here's an example of ocean-ocean convergence where we have the Pacific plate and the Philippine plate coming together. The Pacific plate is more dense, so it subducts. On our subducting plate, we create the Mariana Trench. And on our non-subducting plate, the Philippine plate, we create the volcanic island chain called the Mariana Islands. The Mariana Trench, by the way, is the deepest place on Earth. So here, again, we get subduction. This is when a plate goes down into the mantle and is melted, right? So because it's melting, we're forming a magma chamber down here, creating volcanoes. And because we have this plate that's subducting down into the mantle, we can have earthquakes occurring anywhere along this boundary. So if we have an earthquake up here, it would be shallow, but we can get them even, pretty deep down. And so at convergent plate boundaries where subduction is occurring, our earthquake focus is going to be a range, right, from shallow to deep. It can occur anywhere along that subducting plate. With ocean-continent convergence, the oceanic lithosphere is always going to subduct because it's always going to be more dense than the continental plate. In this example, we have the Nazca plate and the South American plate. Nazca plate is oceanic lithosphere. It's getting subducted underneath the South American plate. On the subducting plate, the Nazca plate, we get the Peru-Chile trench. Right? This plate's getting subducted down, melting, creating a magma chamber, which is creating volcanic mountain belts on our continent, on our South American plate. Right? So that's here, South America. So again, we get subduction of the oceanic plates and formation of a volcanic mountain belt on the continental plates. And again, because we have subduction anywhere along the subducting plate, we could have an earthquake occur. And because of that, we have a range of earthquake depths from shallow to deep. And then with continent-continent convergence, again, this is where two continents are converging, as with the Indian plate and the Eurasian plate. Here, right where Asia and India come together. And because of that, we create the Himalayan mountains, right? Because neither one of the plates can subduct, they just run into each other and crinkle up and create tall mountain belts, right? So continental lithosphere cannot be recycled down into the mantle. And so instead we get over thickening of the lithosphere and very large mountain ranges. Because we have this severe crinkling, right, wrinkling happening, we get very severe earthquakes. They also occur relatively shallowly, right, because we don't have subduction happening. but they can be intense. And then at our transform boundaries, again, this is where we have two plates sliding against one another. This is generally on land when we're talking about transform fault boundaries, and continent. Well, obviously, see, this is an example of continental. Sorry, I didn't read that part. On the continents, when we have transform fault boundaries, we have two continental lithosphere plates, like the Pacific and the North American plate. We have like basically a little teeny tiny part of California that is a continental lithosphere on the Pacific plate. And as the plates slide against each other, you can create very large earthquakes. And then when we have transform boundaries at the mid-ocean ridge, right, so when we think about mid-ocean ridges, think about these as mainly being a divergent boundary, but because the Earth is a sphere, we have to break the divergent boundary off by these sort of transform offsets, right? So here's a divergent boundary, here's a divergent boundary, and then in between them is this transform fault. And again, this is where we have plates just sliding past each other. And in the case of mid-ocean ridges, it's just to offset that divergent boundary because it's a sphere and it's really hard to put, right, this sort of flat motion onto a sphere. Cool. We will review whatever you want to about plate tectonics in class on Monday. And then we will also, in lab, we will talk about like how plate tectonics theory came about. And we will practice like describing the different motions and identifying them on a map and those types of things.